mentioned the IMS data, and yeah, some of you also raised your hands when we yeah, asked who has an instrument or who's already has worked with ion mobility data. So yeah, most of my PhD I've been working on implementing ion mobility support for MZmine. And first of all, do you know what or have you heard of ion mobility separation before? If you haven't heard, please raise your hand. Okay, so just a short introduction. So the ion mobility is another form of separation. So it's not like a time of flight separation or a mass to charge separation as our mass spectrometer does. And it's also not that type of separation as we do in our HPLC with interactions with the mobile phase and the stationary phase. So most of the time, or like the ion mobility types that I know, always work with ions in the gas phase. And then there are multiple approaches on how ion and gas molecule interactions can separate your compounds. Some of them have drift tubes where you have like a meter or multiple meter long tubes. You have a stationary gas in it, so it has like a few millibars of pressure. And with electrical fields, you pull the ions through that gas. And due to the collisions of the ions and the gas, you get also some kind of separation. And basically, the separation you get separates the ions on their charge to size ratio or size to charge ratio and the interactions with the gas. So it's basically the bigger the ion is, the more interactions it has with the gas, and the smaller the ion is, the less interactions it has. And then also like you can have electrical fields and moving gases, but basically the ions are separated in the gas phase, and these separations are built into the mass spectrometer, for example. So that means, it's like a different system. You don't need to couple anything or so. It just either is included in the MS or not. And the nice thing is about the ion mobility separations, they can take place in a couple of milliseconds. So if we imagine chromatographic separation, our peak has like a width of, I don't know, like 4 to 5, 6 seconds, depending on how fast your LC is. And then our mass spectrometer, for example, QTOFs, one transient takes, let's say, around about 100 microseconds. So there's a few decades, a few factors of magnitude in between those two time frames. And the ion mobility separation fits in nicely between them. So for every ion package, for example, that comes from the LC, we can then do one ion mobility separation. And this is what happens in here. And then we need a really fast mass spectrometer to separate these ion packages and say, okay, these ion packages have these mobilities or these drop shadow, or like are these big. And so what you get in the end is higher dimensional data. So every extracted ion chromatogram that you can see on the top here is also separated in mobility dimension. And for example, if your LC method wasn't suited to separate some isomers and they elute at the same time, they might have different sizes. And so in the end, the mobility separation is then able to separate these two compounds where the LC was not able to separate them. I'm not saying that it works 100% of the time or so, but it can give you some more information if you have like, if your bioactive compound consists of 2 isomers or more or less. So, and in MZmine, we implemented everything that we cannot just only resolve features then in retention time dimension, which is on the x-axis, but we can also afterwards separate the features in the mobility dimension. So every feature has like multiple dimensions, and we can resolve all of those isomers. And I really hate the next slide because Robin put my face on there. And so at some point we were like, okay, now since we have the ion mobility dimension, And we also support imaging. Let's just use the imaging and mobility data and use that to align LC and high mobility data, because then we can't just align on master charge, but also on the mobility values, which gives us a higher confidence, because then we have two variables that we can assign our molecules on. And that's also something that was like one of the main topics in the MZmine 3 paper, because we were then able to align multi-imaging data sets, so spatially resolved images, and use the fragmentation data that we get from the LC experiments to identify compounds in a more in a better way with higher confidence. I don't know if we have another slide. Yeah, so I told you I hate that slide. And what it looks like in MZmine in the end is that the feature table, since everything, Robin loves it. Since like in the MZmine feature table, we can then in the end combine all those different modalities. So we have the shapes that we also had with our LCMS analysis. We have the ion mobility separation over here, and then for our imaging files, we also have the spatial distribution of our compounds aligned to the LCMS data over here. And then we, since this was a lipid data set, we were also able to use the lipid annotation module in MZmine. So if you do, for example, lipidomics analysis, that might be worth checking out for you, which is also currently under redevelopment by the developer. And this is how it looks. And afterwards, we were then able also to generate molecular networks just from the LC and the MADI data and say, okay, for example, these individual nodes also have a spatial localization and distribution associated with them. Yeah. Is any one of you actively using ion mobility in his lab? What are you using it for, just out of interest? Okay. Okay. Yeah, maybe might also be interesting for you, because then you can use the same software for all your data sets.
Yeah, and
by MS2. So CCS matching is currently not included, because then we would also have to predict the CCS values. The thing with the lipids is that you can say, okay, for this lipid class, I expect these fragments. And then you don't necessarily need a spectral library, because they it's basically like a rule set that you can say, okay, this lipid, for example, this phosphatidylcholine in positive mode has to produce the phosphatidylcholine head group fragment, or in negative mode, we also need to see the fatty acid chain fragments. And if the fragments have these master charge ratios, then it must be this fatty acid. So that's basically like a computational spectral library. Yeah.
Yeah, maybe to focus here on like IMS. So who's kind of thinking about using IMS in the future? Okay, there's a few more people. And I think also like Alan, at least, if I got him right in this slide, he was putting like the Orbitrap or like the Q-tops and so on, more like on the left side on like, we want to discover new things. And then the timsTOF, he put kind of in between verification and also like finding new things. And I think that's mostly what I would also, you know, kind of not, yeah. So so and that's also where I would place it, right? Because we have this additional dimension, which is nice for annotation, and we have one more orthogonal property. We kind of have to ask ourselves, like, how orthogonal is the shape of a molecule really, when we already measure other chemical properties like the mass charge ratio? Like, it kind of coincides and kind of like goes, we usually see some trajectories in the plot, but still, I want to highlight that it's very nice for validation of your annotations. But there's a lot of trouble that comes with IMS still. Yeah, so it's not like super established methods. Yeah, so we're still like, all the labs are still developing methods to really how to handle even like smaller sample sets, like the 88 samples that we did today on like all your little laptops. Like it's way harder to do that with 88 timstamp files because they are massive. And that's also why we support the native format, because converting them to MZml is really exploding the file format even. And so I just want to stress, like very often, you know, with the QTOFs, with the Orbitrap, with the higher resolution mass spectrometry, you can already do all this non-target metabolomics. And then for some compound classes, or maybe for validation, TIMS or IMS in general might be very, very nice to like kind of separate it more and find some new things. And there's specialized application and so on, but at least like the very general workflows, I would not want to process 1,000 timstamp files right now. Like the infrastructure for computing and so on that you would have to buy, and that you will have to kind of maintain and so on. Just wanted to say that. And maybe, if someone already had some like great experiences also, I mean, we use it in like Uwe's lab in Münster also, and we had some great experiences of like tuning the instrument to the last, and then really separating some different isomers, maybe even like where the protonation sites on the molecule, you can sometimes even tear apart and see that there's multiple different ways how to protonate a molecule. And that can be very nice, and it can be just a lot of duplication of problems. Yeah. So, but yeah, like we were definitely able to find great ways to separate compounds with it. But yeah. Okay, so anyone has some like stories of IMS or anything for IMS to share, or questions? Last one.
You mean for IMS? Yeah, so we also support IMS from MZml files. It's, I would say, yeah, it works. It's not as straightforward as with the timstamp files, but we also have a wizard for that. So basically, if you drag and drop your files, now I need to
exit.
Yeah, and I need to share the correct screen again.
Okay. I think it does that if you just cancel it.
Yeah.
Hope so.
Can you see the correct screen, like the PowerPoint screen on the Zoom? Can you?
I think you broke it.
Okay, then I just reshare. So you should be able to see the MZmine now. Okay.
Duplicate.
And
duplicate?
okay, yeah. Okay, so in the wizard, for example, you would have the option for DT-IMS, which would be the drift tube mobility that Agilent uses. You then get a second or a third or another tab here, where you can put some rough parameters for the resolving, because as I showed here, we not only need to resolve in retention time dimension, but we also need to resolve in mobility dimension afterwards. And the rest basically works the same. So you can then import the data files. You set the LC parameters. You set it for the drift tube. And if you do data independent acquisition, you can select DIA here. As we usually say, the data independent features are new in MZmine. There's a software that has been specifically developed for it. But we have something. If you test it out and let us know in the end if you had good experiences or bad experiences with it, that would be great. But you can basically process any vendor's IMS files.
Yeah.
And yeah, if you do, as Robin said, want to process timstor files, then we recommend to use the actual raw data.
Yeah, and so it's already a very long day, and I don't feel tired at all, so I'm still awake. So usually, you know, like with those developer conferences and stuff, it's kind of like everyone can decide to either join the next few slides that I want to show, or if you feel a bit more tired and you want to kind of discuss in some groups, definitely feel free to go out and just, you know, like bunch up outside if you feel like you need a breather and you really need to kind of like take a little break and just talk with some people. Yeah, so just one thing, because we still have time, we also plan to show it, and we hope for having that time. We already mentioned it a couple of times, is the still on. So is the generation of reference data. Yeah. We're also going to share all those slides. So if someone feels like they're going to miss out, there's going to be the recording, and there's also going to be the slides that you can follow along. And I have to maybe say at this point that we're going to share all the slides from like the MZmine sessions. And we have this little license slide here, and I'm just going to explain it so everyone knows you can freely use those slides. You can freely explain molecular networking, feature finding, MZmine, whatever, to other people. Don't even have to show this slide. Don't even have to mention us, right? But just if you want to share the file with other people, like some of the slides that we made with other people, please just share the slide with it so that people know what the license of the slides are. And also, if you add some new slides, maybe send them back to us, and also put your face in there so that there's more faces and we can expand. Because we have like a bunch of like clean segments, I call them, and then you can just use them and just, you know, like we don't have to create new slides all the time. So, okay, again, give you like 1 minute to stand up and go outside and talk if you want to, and you can take a breather. And otherwise, I jump into this like generation of spectral libraries. And this is really like in like conferences in our field, it's not very natural to just go out, and it feels weird. But in like engineering, computer engineering and so on, it's very normal. Like there's basically also very often no real schedule, and then you can just like jump into sessions and just, you know, don't want to get rid of you, but just wanted to tell you. Of course, that's why I have you. Also because Stefan did not want you to see it. I thought it was very funny. And I love this slide because he really put all his brains into developing all those tools. And he also measured brain. And that's very funny to me. And I'm a very not so funny person. So, you know, and all credits go to Corinna because she had the idea. I just wanted to let him fly through the screen, and that was kind of childish, but this was actually like on spot. So thank you, Corinna. And also thank you to Corinna because the things I'm going to present are also like his, like her research project. Let's see. Okay, so I hope that I don't bomb it. So let me go here. So, okay, so in this project, we're trying to streamline the whole process, how we build reference data and how we share it. So the idea is in all the labs around the world, we produce data over data. And of course, there's massive, and there's some repositories where you can put raw data, and it's very useful to me because I can then search in that data and I can try to find this one spectrum that looks very interesting to me. I can find it in your data, maybe even reach out to you, start some collaboration. But it's also important, like we buy some compound libraries, and now the struggle starts, you know? Like, we want to measure those compounds, we want to directly like extract the spectra, push them into a repository, but what is the standard way of doing that? There's like mass bank, there's GMPS, so there's many different ways, yeah? And so with Corinna, like this is all still kind of old. This is like 10,000 compounds. So we bought a compound library of 10,000, and it was 3 plates, and she measured them in positive ion mode in 3 days. And then of course for negative ion mode, plus 3 days. Yeah, so it should actually be like 6 days then. And now we actually expanded already to 15,000, but the data that I'm showing is on those 10,000 compounds. And in each well, there was 10 compounds. So during the like processing, we basically only had to inject, of course, a portion of this. If we now look into the molecular networks that we also produced, and this kind of looks different than what we used to see before, and it's because it is produced by MZmine actually, which is another tool that we support out of MZmine. So we export everything for GMPS, we can plug it into MZmine, and then it also computes the spectral similarity like molecular networking, but it visualizes it in a t-SNE plot. So it's a 2D visualization of all the similarities. And now you might ask me, is it better than molecular networking? No. Like, is it different? Yeah. Because to me, at least, those 2D representations of a very, very high dimensional space is very hard to do, right? There's like spectral similarity. We saw that for those polyphenolic glycosides, right? There is some similarity of the glucosides to polyphenols and so on, but then in the end, there's also similarity to so many other compound classes. And in this view, usually things that are close together, they should be very similar, but there's no way to see that something that is up there might also be similar to other things. Yeah, just want to make you aware that all the representations flatten a very multidimensional space, and it's very hard to do. And the whole idea that I didn't tell about was the annotation rate here was actually quite low. It's a very easily purchased compound library from a company. And we got like 50,000 MS2 spectra, and the annotation rate of those MS2 spectra was only about 14%. Yeah, so for known compounds, that kind of feels very low, but might also be because we use different fragmentation energies, and maybe they were also not covered in the public spectral library. And GMPS currently only houses about like 20,000 unique structures and 600,000 library spectra. This is a very low number, I would say, like comparing to Coconut and all those like compound databases, biodatabases that host way more structures in their databases. And so hopefully together, we can expand that. And if we just zoom into this view, we can also open the spectral networks that we did before, molecular networks, and we can see that some of those networks here are not annotated at all, but we have the structures because they came from the company, and we see that they are actually from the same compound family. But yeah, no annotations, few annotations, and here metoprolol is actually very much annotated. So there's many different varieties, very many different molecules here, and they all, like most of them were annotated. So that already shows us that there might be some bias, of course, to compounds that are very easily bought and very easily accessible, and that also then later play a role when we train models and so on. And so now looking back to the world and considering that there's so many mass spectrometers standing around, we would definitely like to leverage all of you to just have compounds, maybe being able to even produce new standards, right? And then measure them, and we facilitate the whole process. And one thing that's very important, there's not one method that fits all. So there's GC-AEMS, maybe even chemical ionization for GC. There's LC, IMSMS, and also MSN. Yeah, so there's multi-state fragmentation and different fragmentation techniques. So maybe you have a different instrument that supports UVPD and other techniques. We want all that data. Yeah, so we want to collaborate with people and then really get like the best, of all instruments. And going into MSN. I'm going to skip over very quickly. We can, again, do like multi-stage fragmentation. So we select a precursor and then select the next precursor and so on. And because Corinna is very interested in if that actually helps us in annotating the compounds more thoroughly, and maybe annotating even like substructures, she developed a method here. So if you want to do the same, you can reach out to her. And it's not very applicable to LCMS, but it's very much more a structural elucidation method. Yeah, so we really stretched out the chromatogram by using a double pump. You can also do that with a single pump, but we use a double pump and then modulated the flows so that we can stretch out the flow, have a very long, stable ionization of the same compounds, and then a quick flush out. And then the whole pipeline kind of looks like that, and it's always moving. But on the top side, you can see that there is the metadata cleanup, because from that company, we actually got a very bad metadata sheet with a lot of errors. Yeah, so they gave us structures and in what well, which structure was present. And then they also gave us neutral masses. So we thought, oh, that's nice. Like we can directly start with an inclusion list and we can do things, right? No. So the structures were salts. And once you dissolve them, they're no salts anymore. So, and also when you measure them, you're not going to see something like tartrates, something, you know? So we really had to like clean up the structures, kind of harmonize them, calculate the neutral masses, and then we can plug all this into MZmine. And we can also produce an acquisition list. Yeah, so if you want to set up your sequence, so far we're doing it on an Orbitrap instrument, but also if you're working with other instruments, we're very happy to help you to really just set up your sequence so that in the end, all the file names contain a unique identifier for your compounds. Yeah, so there's 10 compounds in there, so 10 times a structure linked to a unique identifier, and then we can measure multiple times and get multiple injections in. And then we have structure, like then we annotate the structures, we extract data in MZmine and export everything to a library. And this kind of looks like before. So we set up a workflow, and there's a wizard also for library generation for GC and for LC and so on, IMS. And so the only difference is, of course, like what is your data type? So if you have, for example, ion mobility, we're going to do the whole workflow there. If it's MSN and we don't have any separation, we're just going to build MSN trees and then export all the spectra for MSN. And also do some spectral cleanup and so on. Yeah. And so in MZmine, you've seen MZmine now a lot. There's then like the shape here with a direct infusion, and there's all the different compounds that we annotated, and also some scores that we calculate. And we already looked at this score, for example, like the purity of the isolation. And so if we look at the purity of isolation, there's a clean spectrum, for example, just the isotope pattern. And then here at some point, you might be saying, okay, this is very likely a chimeric spectrum. But the question is a chimeric spectrum really that bad? You know, isn't it better to just have it, but maybe just flag it? And that's basically what we do, right? So I don't want to tell you that I know how to process spectra. I just want to tell you, I did process my spectra with those settings, and this is the library that I exported, and you can use it, and you know what happened to the spectra. Yeah. And in the next step, we can also go through and maybe do some sanity checks on the spectrum. For example, if we have the molecular formula and the structure, of course, we can go through and then just say, okay, there's a lot of water losses here, and maybe we can annotate all of the different signals. And those annotations does not need to be correct here, right? So we really, it's a very simple filter. We just say, but we should at least be able to give it like a sub-molecular formula. Yeah, we don't do much sanity checks here. I mean, we do want to improve on that. And there's actually going to be a hackathon in Barcelona that any one of you who's like coding can join. Hackathon Barcelona, you can check out. And then join us on like spectral quality discussions, developing Python tools, R tools, MZmine, Java, anything. Yeah, so you can join there online or in person. And so here, like we very much like try to expand on this like spectral quality and sanity checks. And we can say here, just like for this like sub-formula level explanation for all the signals, we get like some very high numbers, at least, which are expected because it's a very low filter, that we can at least explain all of those signals. And then also a question that is always coming up is like, how do we merge spectra, right? Right now, let's say we measure in 3 different energies. And for this project, we even measured in MSN. So there's going to be a lot of spectra being generated for one compound. And our approach is that we use all the spectra with different energies. We merge them into individual spectra for low, medium, high energy. And then we merge everything into one spectrum. And then we might even go through the whole MSN tree and merge everything into one spectrum. It's nothing that you can acquire in any way, right? But at least it's going to collapse all information into one spectrum so that other tools might be able to use that. And so this is one way how we try to generate the spectra and then export them so that people can actually use them. And not going to go into detail here. We did the 10,000 compounds first, but those numbers are kind of outdated because we already cleaned up the metadata more. But even with this like not clean metadata, we got like 7,000 of those compounds matched. So we got MS2 spectra for like almost 70%. And in the future, we think that like just working together as a community and really being able to push those spectra very easily is going to be like so much of a booster to all the AI, machine learning, and annotation tools that are being developed. Because right now, we don't really know where the spectra come from. Yeah, so on GMPS, there might be some spectra that are still profile mode, that maybe the metadata does not match up. And there's like a lot of things that just happen because we made it very easy, because otherwise people, it's not that people don't want to share, you know, but it's really, it needs to be kind of easy and it needs to be comprehensible, because you shouldn't do like just a PhD degree to just push data somewhere, right? So yeah, really, we hope that this makes it very easy. You can reach out to us if you have compounds, if you have data already acquired. You can reach out if you want to acquire data or something, or if you want to share compounds. We're also able to facilitate that. We have a network of people that also have machines and run those standards, maybe on like different fragmentation modes even. And then we can kind of like try to increase the coverage. And yeah, and then like MS2Query that we're also going to hear about, and Series and all the other tools can really benefit from that. And it's going to come back to you, right? Yeah, so that's at least for like the reference data generation.
It's very interesting. Thank you. I have a question, because when you generate this, the work like that, this spectra that are summary of different energies and summary of
like consensus spectra or something.
Consensus spectra.
Yeah.
Did you ever test like what kind of score it gives you at the end?
Yeah, I mean, it's so the question was like, if we merge spectra, if like what kind of scores that gives, I guess, against like spectral library matching and maybe serious prediction and so on. So the thing is really like, there's no standard way of merging spectra. So some people sum them up, some people use the maximum intensity across the scans, because then at least you retain the amplitude. Yeah, so if I just use the maximum intensity in like the 3 different energies, at least that's like the raw intensities that I got from the instrument. If I sum them up, or if I average them, of course, there's going to be some discrepancy, like for like smaller ones and larger ones. We did not really check how much it improves the quality. I know that for Series, for example, they don't really look at the intensities. So they very much say we need as much information as we can get. So more signals is more important than having exactly the same intensities. Yeah, so more signals, more information. So increasing the fragmentation energy and having like multiple ones merged is maybe better.
But what I'm thinking is that could be maybe an experiment and you spike in some compound with metabolomics and then see what kind of value it gives you. Because maybe if you put these into public, and the score is 0.4, then maybe it has a value, like a huge value, maybe like with a special annotation that it's a more
Yeah, definitely. So yeah, it was like if we put this in the public domain and you know, people are going to get low confidence scores, that's already something. I guess that's what you said. But still, it would be good to have some tags and some scores and so on to give more evidence to it. And that's also what we kind of try to do, is really like that people know what happened to the spectra, that we can apply some filtering, we can automatically tag the spectra. And then people can also say, like, I only want the spectral libraries of this person and this machine. And so you can basically filter by metadata and also by tags and say, okay, I want some, you know, like very confident MS2 spectra. And again, I think the development of tools is very much like still in the beginning. Like there's so many tools coming out every year. I'm not able to test them all, but I think many of them are very interesting, promising looking. So I'm have high hopes that like boosting public data in general, but also boosting annotated data is going to be a huge increase. And we've seen that with like also language models and so on, and you know, image recognition, that even unlabeled data is very useful and can be used by people, right? So even mass spectra that do not have much metadata can be useful for people to train machine learning models and understand and make sense of mass spectra in general. So they can generalize from that idea. So we can see what comes up in the future.
You are, as I understood, you are injecting mixture.
Yeah.
10 or
10.
10.
Yeah.
Clone injection.
Yeah.
So, which mode we select the precursors, we fragment it, or we do not?
Okay, that's actually a good one. I wanted to say that clearly, but I did not actually. So yeah, we inject a mixture of compounds. And so many people would be very overcautious now maybe and say, oh, wait, I should have like an inclusion list. I should really like try to set the instrument up so that it really requires everything that I wanted to know, maybe even of multiple different adducts. But we actually did it really just in the data-dependent acquisition mode. Yeah, we had some people that even injected like full injection, and they extract the MS1. And then from that, they did some pre-processing. They did an inclusion list, and then they injected again. But for us, it was really like, why not directly do DDA? And if we miss out something, we're definitely going to do that. We can still go back and do like multiple injections more, but we already have information, and we might even see that some of the fragmentation energies were still too low. Even though using like 3 different energies, we can then go back and say, okay, we want more out of this, and we can go back and inject more. So we really did like a very generous exclusion list. Yeah, so we really excluded everything that was in the bank with like even remotely close to the trigger for MS2, because then we were sure that no trash is going to trigger our instrument. You also have to, of course, like after a few injections, you have to see if something else like arises and kind of accumulates. But still, like static exclusion list and dynamic exclusion list again, combination was doing magic, at least here. Yeah, and you're gonna miss a few compounds. Yeah, but just be bold and just inject stuff and, you know, run some DDA. Okay. 5 minutes. Okay, so I guess it's if no one has any more questions, I think it's time to wrap up so that you also can enjoy the city and this amazing weather. And there's a lot of bathing going on. We saw on the way here. There were some people like jumping naked into the river. So feel free to do that. There's actually very close by. There's like even like one stretch where a lot of people are bathing. There are some food markets very close by, and there's very nice paths like on the rivers and churches. And so yeah, enjoy we see each other on the next day. And I do want to highlight that all of you produce a lot of very interesting files that we're not going to use tomorrow. But, and I have to see if I share the correct screen, right? Danny, do I share the screen? No screen. Very good. Let me see. Yeah, so again, there is this GitHub repository that we're having, and there's the MZmine output folder. You can find it when you just go to the main page, and there's MZmine3 and important notice, MZmine output, and then just download all the files that you have for your group. And we're going to use those for all the downstream processing, okay? Thank you so much. We're going to be around, so there's a lot of questions up ahead, and thanks so much for the very engaging audience also online. It was amazing, and I'm happy that we still have so much time until Friday.